Alright, so I have this little diagram here. It kind of shows you what we're going to be doing. You start out with some function. In this case, it's a function w. And then we go through, and if we have w that is equal to some function, so w equals some function of xy, but then x and y are functions of, let's say, t. And I could see this happening in the real world where, okay, so you have some big function, and then you have that function is comprised of x and y, which are both dependent on time. Like your x is dependent on time and your y is dependent on time. So then how would you find the derivative of w with respect to time? Well, to find the derivative of w with respect to time, you have to take the partial derivative of w with respect to x, and then say that times the derivative of x with respect to time, plus the partial derivative of w with respect to y times the derivative of y with respect to time. So since x and y are both functions of t, or I was calling it time, then not only do you have to take the derivative of the function with respect to x and y, you also have to take the derivative of x and y with respect to time and put those in there. So that's kind of what the chart says.
So both the first ones are partial derivatives?
Yeah. And I mean, x and y here will be functions of time, so they will have only one variable. So for example, let's say that, and I'm going to copy this little example out of the book. This is on page 907. Let's say that our function w is equal to x squared y minus y squared. X is equal to sine of t, and y is equal to e to the t. Alright, and let's see what happens if we follow our formula. So dw dt is going to be equal to, so we want to take the partial derivative of w with respect to x. So that's going to be 2xy, right? And then the next term goes away because the derivative of the y squared term is 0. And we'll say that times dx dt. What is dx dt? The derivative of x. That's just going to be what? Cosine. Alright, and then we say plus dw, or the partial derivative of w with respect to y now. Okay, so both terms have a y, so this is going to be x squared, and then the derivative of y is 1, minus, and the derivative of y squared is 2y. So make sure you put that in parentheses. We don't want to forget the parentheses because we have to multiply it times dy dt. And dy dt here is just going to be e to the t.
So we'll take the derivative of the et.
The derivative of e to the t is e to the t. It's like the derivative of e to the x is e to the x. Now, we have to come back in our final answer and let x be sine of t and y be e to the t. So I'll have 2. Now for x, remember I said I'm plugging in sine of t. For y, I'm plugging in e to the t. And then I already had a cosine of t. Plus, that'll be sine squared t minus 2e to the t all times e to the t. And now I want to do my algebra to simplify. So this would be 2e to the t sine t cosine t plus e to the t sine squared t minus 2e to the, what do I get when I multiply e to the t times e to the t? I have to add the powers, right? So it's e to the 2t. Now, this chain rule formula that we're using is just an alternate way to work out this derivative. In most cases, well, not most, but in some cases, it is simpler to make the substitution into the original function and then take the derivative. Let me show you what I'm talking about. So that's using the formula. So let's say that I started over, except I'm going to plug in the x and the y to start with. I'm not going to wait and do the derivative and then plug it in. So let's do that. Let's rewrite w. So if I plugged in x and y to begin with, I would have what? Sine squared t times what? E to the t. We usually write that exponential in front of the trig function. So I'm going to write it in front of the trig function. So that's e to the t times sine squared t minus e to the 2t. That's right. Power to a power, we multiply. All right. So that's what the function would be if we plugged it in to begin with. Now let's find dw dt. So here I would have to use the product rule. The first term times the derivative of the second term. So that would be, the derivative of sine squared t is not cosine squared t, right? Because you have to use the chain rule there. That's like a u squared, so it's 2u du. So that would be 2, and then subtract the power by 1, and then the derivative of sine is cosine. So that, what I just did was the first term times the derivative of the second term. Plus, now I need to say the second term times the derivative of the first term. So what's the derivative of e to the t? E to the t. Minus, what's the derivative of e to the 2t? The u is 2t, so the du is 2. So this is 2 e to the 2t. All right, now let's do our algebra. There's really only one thing to do. I'm going to write 2 e to the t, and then I have sine t cosine t plus e to the t sine squared t minus 2 e to the 2t. Now compare the two answers. They're the same, right? So whether I make all of the substitutions to begin with and take the derivative, or I follow the formula for the chain rule, I get the same answer. So is one easier than the other? Sometimes one is easier than the other. So I don't know how to, I mean, it depends. If you have more than just, if your function is of 3 variables, then, and you extend that same definition, like if this was of 3 variables here, instead of just 2, it would be easier to do it like this and then do the substitution at the end. If it's of 2 variables, it might be easier just to plug stuff in and then do the derivative that way. But you will get the same answer either way.
Could you use the chain rule formula, and then once you get that answer, just plug it in calculator, the original equation where you just went in and plugged the x's and y's into the normal.
And just check it that way?
Take the derivative of that, check it.
Yeah. You could use a calculator to help check that.
We can do it either way on the test.
I would rather you use the formula on the test. So use this formula on the test, and then, like he said, I would probably punch this in the calculator after you've already plugged it in, and take the derivative of that in the calculator and check and make sure that it's the same thing. All right, let's look at another one. So if we have more than one variable in our x and y, so you remember how x and y here was just a function of t? If you have more than one variable, then you can find more than one type of derivative of w. Let me show you what I'm talking about. So let's say that I want to find the partial derivative of w with respect to s and the partial derivative of w with respect to t for w equals 2xy, where x equals s squared plus t squared and y equals s over t. All right. So what I would do first on this one is I would plug in for your x and your y, since you have, especially since we have more than one variable. Plugging in is going to make this one simpler. This is the way that I would do it, and I'm fine with you doing it this way. So you'd have w equals 2 times s squared plus t squared times s over t. So then I would multiply in s over t. What would that give us? We'd have 2 times s cubed over t plus what? When you multiply this times t squared, it's going to be what? st. So now that I've done my substitution, I can find the partial derivative with respect to s. That just means I need to take the derivative of w here with respect to s. So the 2 is in front, that's a constant. Now how do I take the derivative of s cubed over t with respect to s? The t is a constant, right? So don't worry about the quotient rule. You just do the power rule. So that's 3s squared, and then the t stays in the denominator because it's a constant, plus the derivative of st with respect to s is what? Just t. So that's the answer. Now that's not the most simplified answer. For the best answer, you would want to multiply the 2 in and get a common denominator of t. So if I get a common, I'm going to do a common denominator of t first, and then I'll multiply whatever I get up here times 2. So t will go into t one time. 1 times 3s squared is 3s squared. And then this next term doesn't have a t in the denominator. So you'd have to say t times t. That gives you plus t squared. And so my final answer would be 6s squared plus 2t squared all over t. All right, now let's find the partial derivative of w with respect to t. I'm going to go back to where I've already plugged in for w, and I'm going to take the derivative of this term up here where I plugged in now with respect to t. So the 2 is a constant. Now this first integral here now that s cubed is a constant term, I'm taking the derivative of 1 over t. Remember, that's the same thing as t to the negative 1 power. So that would be, my s cubed stays there. It's the same. But the derivative of t to the negative 1 power is negative t to the negative 2. Right? Or negative, that's right, negative s cubed over t squared.
So why would it be negative now?
When you take the derivative of this, of t to the negative 1, you get negative 1 t to the negative 2 because you have to multiply times the front. So that's why the s squared, the s cubed would be negative. All right, plus, what's the derivative of st? Just s, that's right. So now I would multiply the 2 in and get a common denominator. This time the common denominator is t squared. So let's do both of these at the same time. So that would be negative 2s cubed plus, now since s doesn't have a denominator, you're going to multiply it times the t squared. So that would be 2s t squared. Now, you may be saying, why did we do our substitution first on that one, but we did it last on the very first time we worked the problem, and then we did it? Because I want to show you that whether you do your substitution to begin with, or you follow the formulas that I'm about to give you, you will get the same answer. So if you have 2 independent variables, like we do here, you know, what were our 2 independent variables? S and t. Everything else, x and y depends on s and t, and w depends on x and y, so that makes them also dependent on s and t. So, let me see, I'm going to put that on the next page and make it a little bigger. Here are the 2 formulas, and they're almost exactly the same as before. It's just, okay, if you want to take the partial derivative of w with respect to s, you can do it like this. You can say the partial derivative of w with respect to x times the partial derivative of x with respect to s plus the partial derivative of w with respect to y times the partial derivative of y with respect to s. So if I had the same problem, you will get the same answer that we did on that. So how about we do that? We're going to work the same problem. So we know we're going to get the same answers. Let's just use the formulas to do that first. Or let's just use this formula and try it out. All right. The first way we worked it was called substitution on where we just worked it. Now we're doing it with the definition of the chain rule. So the things that we need for the definition of the chain rule, we're going to need, if we find the partial derivative of w with respect to s, we need the partial derivative of w with respect to x, so that would be 2y, times the partial derivative of x with respect to s. So look at x, take the derivative of this with respect to s, that's 2s. Plus the partial derivative of w with respect to y, that's going to be 2x, times the partial derivative of y with respect to s. So if I take the derivative of y with respect to s, then that's just going to be what? 1 over t, because the t is a constant. So once you follow the formula, then you have to come back in and plug in for x and y. So that will be 2 times s squared plus t squared times 2s plus 2, wait, yeah, I plugged in x. I need to plug in y. I'm sorry. I apologize. So I need to plug in the y, not the x first, because this is a y, not an x. So that's s over t and then bring this down, so that's 2s. So plus 2, now here's where I plug in my x, times 1 over t. So I have 4s squared over t plus, that's going to be 2s squared plus 2t squared over t. They both have a common denominator now, so we can put our s squared terms together and we get what? 6s squared plus 2t squared all over t. Now, let's compare what we just did to what we did before. So I'm going to scroll back up. So before, what did we do? We rewrote w in terms of s and t, and then we took the derivative of that with respect to s. And we got, so we went through and we got 6s squared plus 2t squared over t. Now, what did we just do? We just followed the formula to do the same thing by the chain rule. The only difference is, after we take our derivative and follow the formula, we have to plug back in for x and y. Which way is easier? I don't know. To me, it's about the same. But there are two ways to work this problem. All right, let's do the last derivative. Let's do the partial derivative of w with respect to t. So the partial derivative of w with respect to t is going to be equal to the partial derivative of w with respect to x, so that's what? 2y, times the partial derivative of x with respect to t, which is going to be 2t, plus the partial derivative of w with respect to y, what's that going to be? 2x times the partial derivative of y with respect to t. That may be the one that gives you a little trouble. You may not. Remember, if you're taking the derivative with respect to t, that's like a t to the negative 1. So that one is going to be negative s over t what? Squared. So once you follow the formula, then we have to come back in and plug in for x and for y. So that would be 2 times s over t times 2t plus 2 times s squared plus t squared times 1 over, times negative s over t squared. So that's going to be 4st over t plus, got a lot of stuff to multiply together here. I'm going to multiply the 2 and multiply the negative s in. So that's going to make that a minus 2s cubed. And that's going to make that a minus 2t squared s. And they both have a denominator of what? T squared. So if they all three had a denominator of t squared, what would this first term become? If you say t squared divided by t, that leaves you with t, so you'd have to multiply the numerator by t, so that would be 4st squared, then minus 2s cubed, minus 2s t squared s. Well, the first and last term are like terms, aren't they? Because one is st squared and one is t squared s. So that's going to be 2st squared minus 2s cubed all over t squared. So that one to me was probably harder the second way. using the chain rule. But I just want you to understand that there is another rule. There is another way to do it without doing substitution first. And those rules can be extended to as many variables as you want them to be. You can extend it to 2 variables, 3 variables, whatever. Okay? You just have another part. You have one more part. Like if you have a z in there, you're just going to have the partial derivative with respect to w. I'm sorry, the partial derivative of w with respect to z times the partial derivative of z with respect to whatever variable you're taking the derivative of. So you can extend that. Now, if our equation is written implicitly, do you remember? I know we say that a lot in DE, implicit and explicit. Remember, implicit is if you have the function written of x and y. So like, and here we'd use like a capital F. I know we've been using little f, but like if I had a big function f of x, y, like this. That's an implicit equation. If we have something like that, we have a formula to follow. Because this isn't little f of xy where we're letting like w equal little f of xy. This is capital F of xy. So this is the function. So the difference between the little f and the capital F is it would be like this function here equals 0. Okay? Like an equation. So if we have that, then we can follow this formula. And you know I'm not a stickler when it comes to formulas, especially when you get through Cal 2. I start letting you write down a lot of formulas. So I definitely have these on your formula sheet. If you want to take if you have a function, capital F, which equals 0, that defines a function, then to find the derivative, dy dx, you take the negative of the partial derivative of f with respect to x divided by the partial derivative of f with respect to y. That's really easy, right? We can do this really easy. So let's do it for this problem. Dy dx would be equal to the negative of, now take the derivative of this function with respect to x, so that goes to 0, that goes to 0, that goes to 0. That's negative 2x. Remember I had a negative in the formula. That's negative 2x over the derivative of f with respect to y. That's 3y squared plus 2y minus 5. And then that goes to 0 and that goes to 0. So this negative could cancel that negative out and just leave you with 2x over 3y squared plus 2y minus 5. Now, if you have 3 variables, then you need to use this bottom formulas. Depends on whether you want to take the derivative of the partial derivative of z with respect to x or the partial derivative of z with respect to y as to which formula that you use. And that's actually the end of this section. So that's where we're going to stop.